Um, Here we have another example, a person pushing a basketball. So if you push as hard as you can on a basketball, you can make that basketball really accelerate. But if you push as hard as you can on a big SUV, you can't really make it accelerate that much. It is that inverse proportionality due to the mass. In the end, these two ideas make an equation. The direct proportionality between acceleration and force and the inverse proportionality between acceleration and mass actually just very neatly fit into this equation, which we often just call Newton's second law for motion. And it's usually represented like this: the net force equals the mass times acceleration. But this is a very simple explanation of how force accelerates things. If you apply a force to something, to some mass, it will accelerate it directly proportional to the force and inversely proportional to mass. This equation actually introduces us new units as well. Mass is in kilograms. The acceleration is in meters per second squared, as we know so far. And if you have 1 kilogram times meters per second squared, we call that a Newton. So if you get 1 kilogram times 1 meter per second squared here in this equation, and you get this, that would be 1 Newton. 1 Newton of force. If you want to know how much force that is in a very practical sense, you could take an object that's about 1/10 of a kilogram and drop it from 1 meter onto your hand. So 1/10 of a kilogram is about, see, a 1/10 of a kilogram is probably this thing right here. No, that's a little bit too heavy, I think. 1/10 of a kilogram is probably this laser pointer. So this laser pointer here, if I had 10 of those, it'd probably be close to a kilogram, I'm guessing. If I put my hand down on the floor, lift this up a little over 3 feet, about 40 inches, and drop it on my hand, I would feel about 1 Newton of force on my hand. So, gives you an idea, a little bit of it. We don't like using newtons for measuring weight. And the reason is because in the English system, 1 Newton is about 0.225 pounds, about 1/4 of a pound. So you take your weight and multiply by 4, and that's your weight in newtons. Take your weight in pounds, multiply by 4. So nobody wants to be 1,000 newtons, or 800 newtons, or 500 newtons. That just sounds bad. How much do you weigh? 500. Holy moly. That's actually a really good weight, you know. That's like 100, what's that, 130 pounds. That's an average adult weight, or a little bit lower than, that's quite a bit lower than an average adult weight, probably. But anyway, I think last time I weighed myself in newtons, and I have a scale, I have a Newton scale around here somewhere. I don't know how to go into it. I have it somewhere. I think the last time I weighed myself with it, I was like 1,000, because I'm old and fat. But anyway, nobody likes to do that. But in the English units, pounds are the force unit, and in the SI units, it's newtons. In English, for mass, instead of using pounds, instead of using kilograms, they use things called slugs. So if you want to know your mass in English units, you have to know it, and you have to calculate it in slugs, which also sounds terrible. Why do they do this to us? Anyway. Okay, so mass versus weight. What is mass versus weight? Well, mass is essentially how much matter something has, right? Whereas weight is just how much is pulling on it. Like the Earth is pulling on the moon, it pulls 1.6. It pulls with 1.6 meters per second squared. So you lose like, what is it, 84% of your weight just by going to the moon. But you don't lose any of your mass necessarily. So how do they measure your mass in space, since you're weightless in space, because you're not standing on a scale? Well, they actually just accelerate your body. So you sit in this chair, and then they accelerate the chair by pushing it. They actually vibrate it back and forth. It actually rocks back and forth. But they know how much force is acting on your body. So somebody that has more mass will actually make this chair vibrate back and forth more. And it actually moves further back and forth because it's harder to slow down somebody with more mass. And they have to do that all the time in space because when you go to space, you usually lose bone mass and muscle mass, and they don't want you to. That's unhealthy. So you have to exercise and eat certain things every day, and just to try to keep your bone mass and your muscle mass as high as possible. So when you come back, you don't have to sit in a hospital for 2 months. Anyway, so let's do some examples of calculating things really quick. We've got about an hour left. Here's a person pushing a lawnmower. Very simple situation. The net force is shown here as a forward force like this. But there's actually two forces that are not being shown here that cancel out. How many of you have mown a lawn before? Mown a lawn before? You know that when you're pushing on it, it actually pushes it down into the lawn a little bit, right? It actually makes it push lower in the lawn and mows lower in the lawn. And you can actually lift up the front of the lawnmower and kind of counteract that. And that's because the handle is at an angle. Whenever you push on something, you're always going to apply a force along the direction of the object that you're pushing. It's just kind of a natural thing that happens. So the force that this person is pushing with is actually pushing this direction. But the downward force is counteracted by an upward normal force of the earth. So the lawnmower pushes into the grass a little bit, but eventually it meets the earth and the earth stops it from going down. And those forces cancel out because two forces equal and opposite will add to a zero force in that up and down direction. And then the part of the force, so part of the force is going down, but part of the force is going forward. The part of the force that is going forward is this force here, but you also have some resistive force. Anybody who's mown a lawn knows that there's resistance, so you have to keep pushing, right? So there's a little bit of resistive force. So this net force forward was probably more, and then they had to subtract off a little resistance, right? So they're telling us that the push of the pushing force minus the friction is the net force here shown at about 51 newtons, about 11 pounds, they're saying. And it's parallel to the ground. Then the mass of the lawnmower is 24 kilograms. We want to know what's acceleration. Well, that's a very simple solution to this equation. Acceleration equals force over mass instead of force equals mass times acceleration. Here's the original equation somewhere. Here it is. Here's the original equation. Force equals mass times acceleration. And we solve that for the acceleration here. Now, since we're in one dimension, we're talking about this in 2 dimensions, but since our force is forward and our lawnmower is going to move forward, we're going to consider this a one-dimensional problem. We don't have to think about the vectors yet. We can just solve for the acceleration, 51 over 24 newtons over kilograms, and we get 22.1 meters per second squared of acceleration. And what that means is that if he keeps pushing with this amount of force, after 1 second, if he starts from rest, he'll be going 2.1 meters per second. After 2 seconds, he'll be going 4.1 meters per second. And then he'll be going too fast to push a lawnmower at that point. And in fact, even 2.1 meters per second is pretty fast for a lawnmower. You'd be running, but at 4.1, you'll be running. But eventually, once you get that lawnmower up to speed, you don't really have to push so hard anymore, right? You have to push hard at the beginning. But once you get it going at a good speed, you just kind of have to keep it going. And that force that you have to exert on it to just keep it going is just enough to overcome the friction. All you're doing at that point is you're just counteracting the friction. If you were mowing a lawn on an ice rink, how many of you have been ice skating before? You start pushing something on an ice rink, like a friend, all you have to do is get them started and then just kind of go. You don't have to keep them going, right? And if you do, it's just a little tiny push. Skating, because there's very little friction, requires just a little force to start, and then they just keep going. That inertia takes over, and they just keep doing what they're doing. Here's another example where instead of one force, we're going to have a whole bunch of forces, and they actually show us the weight of the sled and the normal force that's counteracting it, and they also show us the frictional force here. So we have 4 rockets, a little frictional force, and we want to figure out what's going to happen here. Here, what do they tell us? They tell us they tell us the acceleration, and they tell us the opposing frictional force. Okay, so this is what the free body diagram is going to look like. We're not going to worry about the up and down forces because they just cancel out and equal 0. but we have 4 thrust forces going forward and 1 frictional force going backwards. And the equation says the net force, so we have to add them all together. 4 times T minus little f. And that ends up looking like this. 4 times T minus little f is equal to our net force. And then that has to equal the mass times acceleration. And then we solve that, and we're trying to figure out what the thrust is, because they've told us the acceleration. We figure out what the thrust is by getting the thrust on one side, dividing by 4, and we get this 2.6 times 10 to the 4th newtons, which is big, but remember, newtons are small, so you'd expect big numbers for things like rockets. And this comes from actual experiments that were done. They're trying to test how much acceleration a person can actually handle without dying. And they had one guy that got to, I can't remember exactly how high, they say here, accelerations of 45 times g, so about 450 meters per second squared of acceleration. And the guy was like bleeding in his face because of all these blood vessels that burst, and his lungs were like, he had edema in his lungs, which was burst blood vessels in his lungs. All these terrible things that happened. And he recovered. It took him a couple weeks to recover. But he didn't die. Holy mackerel. What kind of person do you have to be to want to do that? I volunteer. He was an Air Force pilot. That kind of tells you something, I guess. Especially Air Force pilots back then were kind of crazy. Okay, so now the last law, which is probably the hardest one to understand, but also one of the simplest laws. It's the Newton's third law of motion, and it's actually one of them. This is a weird thing because this is a law that almost everybody knows, but almost nobody understands. So if I start this phrase, you can almost certainly finish it. For every action, there is a, what's the end of that phrase? You ever heard that phrase before? For every action, there's a reaction, right? That's what it is. For every action, there's a reaction, and that's what this law is. That's where that phrase came from, is this law. But very few people understand it, what it really means. But I'm going to take you back to my mosquito example. And that's the reason I like to use the mosquito example, because it's a perfect example of that every action has an opposite but equal reaction. That's how you really need to say this law. For every force is opposed by an equal and opposite force. Why is this misunderstood? This is misunderstood because most people think that means that the force acts on the same thing in both directions, but it doesn't. It acts on different things in different directions. So the mosquito in the truck, as the truck comes along, the mosquito is going to hit the truck. Okay? And it's not going to hit the truck very hard. And you know that because the truck doesn't even feel it, doesn't even notice it. Just keeps going. It'd be very difficult to measure the amount of force that one mosquito exerts on a truck. Very little amount of force. But it does exert a force. The truck exerts the same exact amount of force in the exact opposite direction on the mosquito. And it's not very much force. Why is there such a big difference in what happens? To the truck, nothing happens. To the mosquito, something very big happens, right? Its face meets its butt, right? Why is that such a different reaction, even though it's the same? Newton says it's the same exact force. Let me give you a clue. How are we going to do it on here? Share. Clear. All joined. Here's our truck. I'm not going to draw all 18 wheels. Wow, that's a great truck. Need another wheel up here. Here's our mosquito. Here's our equation. Force equals mass times acceleration. And according to Newton's third law, the force is the same. The truck exerts the same force on the mosquito as the mosquito exerts on the truck. So let's say that force is equal to this force right here, F. That's the force. What's the mosquito's mass? Itty bitty mass. What's the truck's mass? Big, huge mass. If these are going to have a mass and acceleration on both sides, what has to happen to the acceleration for them both to equal this little force? If you have a huge mass and you're going to multiply it by something to get a small number, what do you have to multiply it by? A very, very tiny number. You know, like a fraction of a fraction of a fraction of a fraction. A big number by times a really tiny acceleration over here can still give you a kind of small number. But this has to be really tiny. So the acceleration of the truck is really tiny. The big mass gets a tiny acceleration. But what happens when you have a little tiny mass and it has to be a bigger force than the mass? What has to happen on this side? You have to have a big old acceleration times this tiny little mass to make this kind of, smallish force. So what happens to the mosquito? It gets accelerated so quick that its head gets accelerated to its butt, right? And it becomes much smaller than it was, at least in size, if not in mass, right? Another example of this is I was a swimmer in high school. My best friend encouraged me to join the swim team because he was the captain of the swim team, and he knew I could swim all the strokes even though I wasn't a brilliant athlete. I was competent but not athletic. And so I could swim any race, but I could never win a race. That's what it amounted to. And that's exactly what they needed. So I joined the swim team. And in swim practice, we always had this thing that we cheated with when we would be on kickboards. They'd make us kick like 900 laps. And we would cheat by grabbing each other's hands and pulling each other through the water. As one person was going one way, one person was going the other. My friend hated this. I loved it because I was smaller than he was. I'm big now, but he was much bigger then. He was like Triangle Man with the big muscles. And so I would grab his hand and we'd pull, and I'd go flying, and he'd only make a little bit of progress. Why? Because when we were pulling on each other, it was the same force. Same force, either way. But my mass was smaller, so I had bigger acceleration. And it was kind of fun if you grab the hand of one of the girls on the team. You'd have these girls who are like 88 pounds, and you're like a 160-pound guy. You pull them almost out of the water. Whoosh, you go flying. It was pretty fun. But anyway, that's the same idea here. Now we have to do a demonstration. We have to do a classroom demonstration. This is our first experiment in class. Let's see. I want to change my share. I'm going to go to a new share. Let's see. Let's share the desktop and go to do I have a camera plugged in? I should have. Here's one. Actually, let's just do it in front of the screen here. I've got a thing here. All right. I need a volunteer. Who's going to volunteer for me? Anyone? You're drinking your Powerade. That means you're volunteering. Okay, come on up. What's your name again? I'm sorry.
Briar.
Briar is going to be our volunteer. Here I have just a plain piece of tissue paper. And Briar is a strapping young man. He's got boots on, so we're going to assume he's strong. I want you to break this in half with a karate chop. Can you do that for me? It's just going to break this tissue in. Just chop it? Yep, chop it. Go ahead. What's wrong? Why didn't you break it in half? Try it again. Try it again. Karate chop it. Break it in half. So why can't he break it? He's obviously swinging pretty hard because he accelerates the tissue, but why can't he break it? What happens right before he tries to break it every time? Right? So if I'm dropping it, the tissue can't push back. Right? The tissue has nothing holding on to it, nothing making it push back. Go ahead and sit down. Oh, do you want to break it? Go ahead. There you go. You can keep it if you want. Because, and this is actually very, very important for a lot of things. For example, University of Nebraska has this commercial about these guardrails that they've created for NASCAR. Have you seen this commercial? It's this thing that's bound. They call it. They say it bounces back or whatever. Well, that's not actually the reason that it's safe. They're misrepresenting the science, but they're trying to make it more accessible. But anyway, the point is that what they've created is they've created these guardrails that give, these guardrails that essentially collapse and slow down this thing over time. Essentially, it's like dropping the tissue when you run into the wall, except it's just kind of letting it go a little bit and just catching it, right? And there's other things involved with this. This isn't the only issue involved with these things, but if there's nothing to push back, you can't get hit. I mean, you can't push on something if it doesn't push back. This is why boxers roll with the punches. You ever seen a boxer when they get hit, their head does this super exaggerated thing? That's on purpose. Because if you do this when somebody hits you, not only do you get knocked out, but you break their hand, right? You don't want to do that. In fact, how many of you have seen Cinderella Man, the story about the boxer from New Jersey? You ever seen that movie? Great movie, you should see it. But in that movie, there's a boxer who killed 3 people in the ring. Not because he was mean, not because he was brutal. He was actually a really nice guy, but he was just too fast. He was actually a boxer. His name was Max Baer, and he's actually from my hometown. Believe it or not. My hometown has a lot of weird connections, considering it's just a podunk town. It's like this tiny. It's tiny for California. It's like 80,000 people, but it's like a rodeo town way outside on the edge of the Bay Area, right between like cities and like cows. There's my town, and but he grew up there. They have a park to his name, and I never even knew who he was until I was like in college, and then I watched this movie, and he killed 3 people in the ring because he was so fast people couldn't roll with his punches, and he literally just disconnected their brain stems while he hit them. And I mean, he was a nice guy. I mean, he like paid for their wives' houses and their kids' college and everything, so that they didn't have to suffer anymore. Just he wasn't trying to kill anybody. He just was too fast. But that's why boxers roll with the punches, is so that they can not hit back. You don't want to hit back. And we'll come back to that in a later chapter because it has other implications with things like momentum. So there's our first experiment in class. Way to go, us. So here's another swimming one. Here we have the swimmer who's pushing off of the wall, but the swimmer is pushing towards the wall. So that's obviously not going to accelerate the swimmer. It's the wall that pushes back on them. If this wall was loose and, if you've ever been swimming in a lake and you try to push off something that's floating in the lake, you don't get a very good push, right? But off a wall in a pool, you can get a very good push. This is what we call a normal force. The reason we call it a normal force, you have a normal force is whenever something is pushing against something else, any surface, 2 surfaces pushing against each other, you get a force that is perpendicular to the surfaces, and that's why it's called normal. Normal is another word for perpendicular. And so this person's foot is pushing this way, and so at a 90-degree angle to the surface, the wall will push against her feet, and that's the direction of acceleration. And if you've ever pushed off a wall and you don't push off exactly perpendicular, your feet will slip, right? But your body will still go forward because the normal force is still forward. Now there may be some frictional force, you might pop up or go down a little bit, but you're mostly going to go forward still, even if your feet slip. All right, so here's an example now where we're going to put all this stuff together and try to make sense of some things. We have our professor pushing the cart, What system are we interested in? We're going to do this problem in two different systems. If we do system one, this inside system, we have the professor pushing on the cart and the cart pushing on the professor, right? So the two forces according to Newton's third law. We also have the friction pushing on the cart. But if this is, and we also have the weight of the cart on the floor, the normal force of the weight, the normal force from the floor on the cart as well, those just get canceled out. But if we're just talking about the system 2 here, just the cart, we don't consider the professor pushing on the floor. It's just this one. The professor pushes here, there's friction on the cart, the normal force upward from the earth and the weight downward on the earth, and that's the system. If we consider the whole thing, the professor included, to be the system, then the professor pushes on the floor backwards, the floor pushes forward on the professor. We don't consider this because this is internal to the system now. But the friction is still the floor acting on the cart, so it's still external to the system. So we still have that frictional force out there. And then, of course, the weight and the normal force also. No matter which way you do this problem, you're going to get the same acceleration. Why? Why does this bigger force give the same acceleration than the smaller force for the two different systems? Think of the mosquito and the truck, or the two swimmers, but think of it in a different way. It has a very similar thing to that. In the case of the mosquito and the truck, you had two masses, two different masses, two different accelerations, right? In this case, you have the same acceleration. And what changes? Both the mass and the force changes, right? For system 1, you have a bigger mass. Why does system 1 have a bigger mass? System 2 is just the cart. System 1 is the cart and the professor. The professor has mass. If it's me, it's a lot more mass, right? So if you have more force and more mass, you can have the same acceleration if you balance that out, right? But if you have less force and less mass, because it's just the cart, you can have the same acceleration. So in this case, instead of just changing the mass, instead of just changing the acceleration and getting a bigger acceleration, smaller acceleration for bigger mass, for smaller mass, bigger mass, you change both force and acceleration, or sorry, change both force and mass and get the same acceleration. The way it would look like is this. Let's do this really quick. So we have professor, mass of professor. We have cart, mass of cart. And for in each situation, the acceleration is the same. So we're going to solve force equals mass times acceleration for the acceleration by dividing by the mass on both sides, right? So acceleration equals force over mass now. Same acceleration for both systems, but in one system we have the mass of the professor plus the mass of the cart, right? And that is divided by a bigger force. So essentially you have a bigger force divided by a bigger mass because we're adding two masses together. But on the other side, we have a smaller force with a smaller mass, with just the mass of the cart and just the mass of just the force that the professor is pushing on the cart with. So you can get a small thing over a small thing gives you this acceleration, or a big thing over a big thing can give you this same acceleration. So lots of ways that can happen. So let's actually go and do the problem. In the first one, in the first system, we have the professor pushing on the floor. So acceleration equals force net over mass, and they want us to solve for the acceleration. So we're going to first solve for the net force. The force pushing on the floor minus the force of friction, 126 newtons, The mass is the mass of the professor plus the mass of the cart plus the mass of the stuff on the cart, I guess, equals 84 kilograms total. And you take that force divided by that mass, you get 1.5 meters per second squared. In the second system, where we say that this cart is the system, they want us to solve. They actually want us to solve for the amount of force that the professor pushes on the cart with. So acceleration equals force net over mass is going to be rearranged into force equals mass times acceleration. We have the force that the professor pushes with minus the frictional force equals the net force that the professor pushes on the cart with, or sorry, the net force on the cart rather. And we want to calculate the force that the professor pushes on the cart with. So you solve this equation for force professor, it equals net force plus frictional force. And then that net force is going to be mass times acceleration. So we plug mass equals acceleration into here, and we get mass times acceleration plus frictional force for the force of the professor. And then we do the net. We solve for the net force first. We get 29 newtons for that. The force of the cart and the stuff times the acceleration that we got from the previous problem. Then we solve for the force of the professor by adding the friction on to the net force, and we get 53 newtons. So 53 newtons. Notice that in this problem, she's pushing on the floor with 150 newtons. So this force that she's pushing this way with is 150 newtons, but here it's only 53 newtons. So this one's 3 times bigger than this one. And if you've ever pushed things around on a cart, you'll know that. You'll know that your feet get tired more often than your hands do. That there's a lot of force going on there. All right. That's enough for that section. How much time do we have left? Excuse me. So that's Newton's third law. Now we have all 3 of Newton's laws. We have Newton's first law. First law says that things keep doing what they're already doing. We have Newton's second law that says force equals mass times acceleration. Net force equals mass times the overall acceleration. And that has to do with magnitude and direction. And then we have the symmetry of forces, or Newton's third law, or the law of equal and opposite. Every force has an equal and opposite force. But you have to remember that it's not on the same object, by the same object, right? 2 objects exert forces on each other. One of them is going to exert a force on the other, and then the other is going to exert a force on the first one. Those forces are going to be on different systems from different systems. The 2 forces are never within the same system. Don't confuse that, because then you'll have forces canceling out where they shouldn't, right? But it's a very common mistake to make. Here's a great example. The Earth and the Moon are held together by gravitational forces. So what does that mean happens to the Earth as the Moon goes around it? So we always think that the Earth just goes around the sun just in this big circle. But it's actually not true. This is more what it looks like. That's not a very big picture. But this is more what it looks like. The Moon is going around the Earth, and it goes around the Earth 12 times per year. So in some parts of the Earth's orbit, the Earth is closer to the sun, like in this part of its orbit, where the Moon is actually on the opposite side of the Earth. So the Earth, so no way, that's not right. When the Moon is on the same side, this is actually not correct, I'm thinking. When the Moon is on the same side as the sun, it actually pulls the Earth towards the sun more. So this one should actually be over here. That's not only a bad picture, but it's an incorrect science picture. But essentially, when the moon is on the same side as the Earth as the sun is, the Earth will be closer to the sun. When it's on the opposite side, it's like it's pulling it away from the sun, and it's going to be further from the sun. So it actually has a funky orbit, and all the planets do that have moons. And it's actually even weirder than that. I mean, here's the orbital path around. Since it's not perfect, it's not a perfect 12 times per year. It changes year to year, so it has these weird orbits. And this is another thing that Newton actually was able to figure out from Galileo's observations. So he did a lot of work. Here's another way to think of it. The Earth, as the moon goes around the Earth, and the Earth goes around, it vibrates kind of back and forth in its orbit around its normal orbital path as well. But the most extreme one is is all the way out at Pluto. Pluto is so far out, and actually here's another. Pluto is so far out and so small that its orbital path can be really affected if Uranus, is Uranus the closest one, or Neptune? I can't remember, whichever one is closest to it out there, is close to Mercury, is close to Pluto. When Pluto gets close to the other gas giant that's out there, it actually gets pulled so far in that it actually gets pulled closer to the sun than that last gas giant out there. So Pluto's not the last planet anymore for a while. And it's only happened once in like the past 900 years. But it has happened, and we have been able to measure that. So Pluto has this really funky orbit that's sometimes it makes it the 8th planet, sometimes the 9th planet, or planetoid, however you want to think of it. So it's really funky. Anyway. So what kind of forces have we talked about so far? We've talked about normal forces. Here's our bow wow chow. Did you know that Purina makes lion chow for lions? They make dog chow, and they make lion chow, and giraffe chow. They make all kinds. I know that because I watched a movie. Anyway, bow wow chow. You put it on the table, and the table exerts a force. The hand, when you're holding the bag, exerts a force. When you put it on the table exerts a force. And you know that because sometimes the table is not strong enough to exert that force, and it breaks. And what does the bag do? It falls down to something that does have enough strength to exert that force, right? The normal force. Free-bodied objects. But here's an example where the normal force starts to get funky. The skier. How many of you have been skiing? Nobody's been skiing before? Well, I've only been skiing a few times. But I've been on snow a lot. But anyway, on mountains a lot. But so what happens on an incline? Well, the normal force is always perpendicular to the surface contact. So the skis are in contact with the slope of snow, and this is the perpendicular line now to that surface contact. So the normal force is actually in this direction, which is good because this normal force direction is not enough force to hold the skier up. There's a little bit of leftover force here. Here's the weight of the skier, and we're going to break this weight into two perpendicular forces. One that is perpendicular to the surface and one that is parallel to the surface. So if you add these two weight forces together, that equals the total weight of the skier. This one right here is the weight that pushes the skier down into the hill, but this part of the weight is the part that makes the skier slide down the hill. So this force is pointing down the hill, and that's what causes him to ski, right? If you're not on a hill, you can't ski. You just, well, unless you're cross-country skiing and you're making your own forces by pushing backwards so that the snow pushes you forwards. But this is an example of what we call a rotated axes problem, where normally we have X and Y, in the vertical and horizontal directions. We're going to create a new set of axes that are actually parallel and perpendicular to our surface, because our surface is not exactly horizontal. And why would we do that? Because gravity still pulls straight down. Even if you're on this hill, gravity's not pulling you towards the hill, it's pulling you towards the center of the earth. So it pulls down this way. The weight forces this way, and so we create an axis that is parallel and an axis that is perpendicular. And instead of having X components to our vectors, we're going to have parallel and perpendicular components to our vector. And the friction is going to actually act parallel to the surface, so that's nice. The friction is just in the parallel direction. The normal force is going to be in the perpendicular direction. And we only have to resolve one of our vectors in two components, this weight vector. And if we can find out what this weight parallel force is, and we can subtract off the frictional force, we'll know how much force the skier is feeling, and we can calculate how much acceleration they're having. Or in this example, they're actually trying to figure out, no, actually, no, that's right. They want to know the acceleration if the friction is 45 newtons. So they want to know what is the acceleration if the friction is negligible, in other words, if the friction is zero. So how do we do that? In this case, the angle that we're using is this 25 degrees here, which is the same as the 25 degrees here. Now, most students have a hard time making what's the word for that? Not geography, it's geometry. There we go. Sorry, my brain stopped for a moment. Most people have a hard time doing the geometry, figuring out if this angle is 25, what's this angle? But it's really quite simple. It's, let me see, let's go to, oh crap. I've been talking in the book and been showing you the whiteboard. Sorry, Brittany. This is the problem we're doing as the skier in the book. Hopefully you've been following along and I haven't confused you too much. Are you still there, Brittany? Can you hear me?
Yeah.
I'm sorry for being on the whiteboard. If I do that again and you can tell I'm talking about things in the book, just tell me to fix the screen so I'm back on the book.
Yeah, okay.
I do that from time to time. It's very easy to do in Zoom. But anyway, if you're doing this sloped version of a coordinate system, it's often a really good idea to draw a really extreme triangle. Oops, that's not what I wanted to do. So if I draw a really extreme triangle, like a really small angle at one end and a really big angle at the other, and then I draw my skier on here, and I show their weight going down this way perpendicular to this, so it's 90 degrees there. It actually becomes really quite obvious when you try to draw the horizontal and the parallel and perpendicular components. The parallel component is going to come out this way, that's parallel, and the perpendicular, well, shoot, I'm doing a bad job drawing this. Try it again. Maybe I'll use straight line drawing. There we go. That's nice. Okay, now we'll do a better job. So this person's weight is still going to be straight down. Still going to look straight down like this. That will be their weight vector. But we need a perpendicular and a parallel vector. Perpendicular, of course. Oops, dang it. Perpendicular will, of course, be just perpendicular to the surface, so 90 degrees to the surface like that. And then the parallel one will connect these two down here. Like that. So if this is our weight vector, then this would be our weight perpendicular because it's perpendicular to the surface. And this would be our weight parallel because it's parallel to the surface. Where our parallel direction, perpendicular direction, man, it's terrible. Like that. But if you draw this triangle very extreme, you can tell that this is the small angle. So that would be my 15 or whatever degrees. And this one you can tell is the small angle would match up with that small angle there. Would also be 15. Okay. Now I can't emphasize enough the use of, oh, that reminds me. I had a student asking about using, so let's go back to the desktop. I can't emphasize enough the using of videos to help you out in this class, but there's also another resource I want to show you really quick. Let's see, can I get into this? So, There's an online tutoring system you can use. And you can find that at Blackboard. So if you don't know how to get onto Blackboard, it's the same password and email as you get onto your email with. You'll just go down here to sign in with third-party account. So it's mpcc.blackboard.com. Then you'll do central login for faculty and students, and it will take you to a page and use it same as your email for the college. Same login for your email. And then on your front page as a student, you should have a link to what's called, I can't remember. But I can show you here. It's called BrainFuse. So you should have a link that looks like this on your main page. And have you tried that? Has anybody tried that? Has anybody been in Blackboard lately and tried that? Anyway, won't let me, have to enable pop-ups apparently. But anyway, here we go. But you can get onto BrainFuse and you can connect with live tutors like 24 hours a day. And I've had several physics students use this for this class, so you can use that as well. And it's free. But also you can just go to the videos in the class, or you can just go to YouTube. So for example, if you're doing a rotated, let's see, we're doing a rotated axes physics or something like this. Just search for that. There are plenty of people out there that have put up lots of videos. Axis of rotation, no, that's not one. You might have to, that's rotating axes, we don't want rotating axes. This one you could use rotation of axes. But make sure that it's the same level as you're using. You don't want to use, for example, on this one, you don't want to use rotational motion. That's like chapter 6 or 7. We'll get to that eventually. But they will have, a better one might be incline physics. It's, yeah, like this one. So here they do an inclined plane problem with friction, without friction, force components. So almost any problem that you find, you can find videos on YouTube. And we're in the process this summer of linking these YouTube videos to the problems within MyOpenMath, but it probably will not be done before the end of the summer. But because we have to find ones that have been there a while and that are really good ones and that will still be there for a long time. But anyway, they are, those things are on YouTube. There are lots of them on YouTube. And I've done some of those. I've actually looked at some of those in the class videos, but I've also made some of those in these class videos. And there are some in the chapter subject videos too. So make use of those. Don't wait too long to find help. Anyway, in this problem, they're using this angle here, which is 25 degrees, but notice that that angle there is opposite the parallel. So whenever you're using an angle that is opposite to the side, that's going to be the sine. So the parallel weight force is going to be associated with the sine. And so when they start putting things together, they have the acceleration in the parallel direction is equal to the force in the parallel direction over the mass. Well, this is just like we did in 2 dimensions with kinematics. You can split your force equals mass times acceleration into x and y. In this case, they're splitting it into parallel, and then into perpendicular, they'll do it later here. So they're doing it in the perpendicular here. So we're just looking at the stuff that's parallel, so we're only going to look at forces that are parallel, and we're only going to calculate accelerations that are parallel. The force that is parallel is the force that mg, the mass times gravity, which is force from the weight times the sine of 25 degrees. So you remember force is equal to mass times acceleration, but in gravity, that means force equals mass times gravity, right? So that's your weight, is acceleration due to, or the force due to acceleration in the vertical direction. And then once they've got that, then they can notice that the force in that direction has mass in it, but also you've divided by mass. So the mass actually goes away. It doesn't matter how much mass you have. All that matters really is the gravitational constant, which is the same everywhere on Earth, and the angle of the slope. Right? So they plug all that in and they calculate, they plug all that in and calculate the acceleration without friction. And then when friction is involved, they use the force equals mass, the force equals, the net force equals the total forces add together, which is that parallel weight force minus now the friction. Here's the weight force. The weight force is pointing in the negative direction for the parallel, and then the friction is pointing in the positive direction. They end up switching that around. It doesn't really matter which way you do it, just as long as you get the difference. So they do the weight parallel minus the force, frictional force, and that's your net force, and then that goes in the equation for Newton's second law. You end up with two forces subtracted from each other to get that net force. And you get less of an acceleration when friction is involved, which is exactly what you'd expect. Now this is a lot of stuff for one day. I want you to remember that we're just trying to kind of introduce you to this stuff. And then we're going to do a lab tomorrow, where you get some experience working with this stuff. And then hopefully you can get started on the homework tomorrow as well, just kind of doing the easier problems. When we come back together on Thursday, we will go over problems that you have questions on, work out some problems together, do some more examples. We haven't quite finished this chapter yet, so we'll also cover the last, these last three problems or these last two sections, are just example after example after example. So we'll go through those examples on Thursday as well. And hopefully give you all that you need to do to finish up chapter 4 by the end of this week, which would be great. And that's pretty much the end of our time today. So go ahead and get chapter 3 cranked out tonight. Hopefully you have enough to do that. And then try to get started today, tomorrow, whenever, on chapter 4. Try to work through some of the simpler problems. Learn about force equals mass times acceleration. Maybe try to do a two-dimensional problem, maybe. See how far you can get. And then we'll come back to this Thursday. We'll see you tomorrow for lab. Have a good evening.
What lab are you doing tomorrow?
Did you have a question? Sorry.
Yeah, what lab are you doing tomorrow?
So tomorrow we're going to do the combining forces lab, I think. And I don't remember which ones I gave. I think I gave you that one. So we started with the introduction to motion last week or 2 weeks ago. Then we didn't do a lab last week, and then this one is going to be combining forces.
Okay.
All right.
Oh, the little cheat sheet that you're gonna hand out.
Oh yeah, I forgot to give that to you, didn't I?
Yeah, I just remembered that.
Okay. If you would email me, just email me your home address. I'll mail it to you at your house. Okay.
And will you be videotaping Wednesday?
Thursday, you mean? Or you mean Wednesday? Right, Wednesday?
Yes.
Yeah, Wednesday. Yes, I can tape that. Do you want me to?
Yes, because I don't know if I will be able to make it to class on Wednesday.
Okay.
If not, I'll email you.
All right. Yeah, that's fine. All right. Sounds good.
Thank you.
Yep.